Hi everyone. I just saw this interesting problem on LinkedIn and I wanted to reply, but suddenly I think I scrolled it and I missed responding in the comment section itself. So I thought I'll make a video on it explaining the problem. From what I saw in the comments in that problem is that there was a confusion when analyzing the circuit when an op-amp circuit goes from an open loop mode to a closed loop mode. Okay, so what happens when such a transition takes place suddenly? Then how do you analyze such a circuit with, of course, energy storing elements in place, right? So you have a capacitor here. So what happens to such a circuit and how do we analyze that? Secondly, does the initial voltage at the output of the op amp have any impact when you do these transitions from open loop to closed loop? Does it have any impact? So we'll try to answer both these questions in the single problem, and I feel it's a very interesting question because it goes through three different modes of operation. As once the switch is closed, it goes through three different modes of operation, and I thought it's a very interesting one. So I thought I'll discuss that for that reason. So the circuit shown here is a non-inverting integrator. You have a capacitor in the feedback path with through a switch. So the switch is open, the op amp is in open loop mode, and at t equal to 0, it's assumed that the switch is closed. Okay, and it's also given that the initial charge across the cap is 0. So no charge is stored across the capacitor. And it's given that the product RC product R into C, which we'll call it as time constant in the circuit, is 1 millisecond. I don't exactly recall the values of R and C, but I'm assuming it's 1 kilo ohm and 1 microfarad. So the product is 1 millisecond. It's also given the op-amp's saturation voltages is plus minus 15 volts. So max it can go to plus 15 and minimum it can go to minus 15. So the op-amp is assumed to be an ideal op-amp. So the characteristics is going to look something like this. So plus 15 and minus 15. So what you are supposed to find is once we close the switch at t equal to 0, what is the voltage across the capacitor after one time constant? So that is at the end of 1 millisecond, what is the voltage across the capacitor? So we'll derive the exact expression for the voltage across the capacitor. So then you can find out, in fact, for any given time, what is the voltage across this capacitor. So we'll start analyzing the problem. So first, I've just said that this is a non-integrating inverter. So you can quickly analyze the circuit. So if I first I'm assuming the switch is closed. So this circuit here, it's a negative feedback op-amp based non-inverting integrator. Okay, so this circuit doesn't have DC feedback. So if you leave the circuit for a long time in the steady state, the capacitor will act like an open circuit. So output would have reached some kind of saturation voltage. So it doesn't have any DC feedback, but it has transient feedback. So which is what will help us in solving this problem. So when the output is undergoing transitions, the circuit will have negative feedback in place. So you can quickly analyze the circuit. The output voltage is given by Vi plus, which is the input voltage here is applied at the non-inverting terminal, plus Vi by SRC. So you have the output voltage has two parts, which is one is the proportional part, which is directly equal to the input itself, and the other part is the integral part. So the output voltage will depend upon the input and its integrated version. So this is a well-known circuit in linear control theory. So it's called the PI control. So where the output of this system is dependent on it's equal to, it has a proportional part of the input and also an integral part of the input. So it's used in is used in control loops to stabilize systems and all that. Also to design the systems to achieve a desired transfer or settling characteristics. So that's the basics about this problem. So we'll now start solving it. So this is the circuit we have. Initially the capacitor, the switch is open, which means op amp is in open loop mode. So we'll assume that no current is flowing through the resistor initially because switch is open. There is no other path for the current through the resistor. So this is at 0 volts. So output of the op amp will be at plus 15. So that's the saturation output voltage of the op amp. Now what happens when you close the switch? So when you close the switch, the circuit reduces to something like this. Now we are supposed to find what happens to all these two node voltages. Now we'll use this simple fact that the capacitor voltage cannot change instantaneously, which means VC of 0 plus and 0 minus are the same. What does this mean is that the voltage across the capacitor is 0, which means it will act like a short circuit. So I can replace this capacitor by a short circuit. The moment you see this, it's very trivial to solve now. What happens in the circuit is that the op-amp is an infinite gain amplifier. So, which means its bandwidth is also infinity. The instant you connect it, it doesn't matter what your output voltage is. Wherever it is, if it's 15 volts, this will also come to 15 and immediately it's in negative feedback mode, in a unity follower mode. So this will come to 10 volts. This node will also raise to 10 volts. So what if you want to, give a very crude way of looking at this, what happens is that the output voltage will start at 15 and jump to 10 volts in the interval 0 plus to 0 minus. It will have a sudden jump from 15 to 10 volts. And the voltage across the resistor, so which is the inverting terminal, will instantly rise from 0 to 15 and then fall back to 10 volts. Because it's in follower mode, both these node voltages will track. So it will also come to 10 volts. All the while, between this interval 0 plus to 0 minus, the capacitor voltage is always at 0 volts. That's not changing. So that's constant. But these two node voltages will change. Now, if you want to understand this even better, take a simpler example like this. Assume that you have an op-amp, which I've shown here. So all I'm trying to show is that the op-amp in the interval 0 minus to 0 plus behaves like this. It's like a unity follower mode. So assume a simpler problem where you just have a switch in the feedback path. And I've connected a resistor R from the inverting terminal to ground. Now this node voltage will be initially at 0 before switch is closed. Now assume that at t equal to 0 the switch is closed. What will happen is that whatever be the voltage at this point, at the output voltage, let's say it may be even minus 15. In this example it cannot be minus 15, it has to be plus 15. It will immediately come back to 10 volts. That is something we are aware of, right? So instantly it's going to come to 10 volts because op-amp's bandwidth is infinity. So that's op-amp reacting to the proportional part. So after that, I'll place the capacitor in place now. So the output voltage comes to 10 volts. So when it comes to 10 volts, this comes to 10 volts. All it's doing is just to follow the input. Because the op-amp is in negative feedback, it will tend to follow the input as it is. This is due to the proportional path, the reaction of the proportional path. Now, after this, the op-amp is in negative feedback, the integration takes place. So in this interval, t greater than 0 plus, integration takes place. So initially output is at 10 volts. So the inverting output is also 10 volts. So you have a current of 10 by R flowing through the resistor that will also flow through the cap. So the capacitor's voltage will increase linearly. So you'll have 10 I by C integral I by C dt is the voltage across the cap. So you will get 10 by RC times T. So the voltage across the capacitor will increase at the rate of 10 volts in 1 millisecond. Times T will be the time domain voltage across the capacitor. So now if you see, when T reaches half a millisecond, this will be 5 volts. So the capacitor will have 5 volts across it. So initially is at 0, it raises to 5 volts at half a millisecond. When it reaches 5 volts, the op-amp's output is now at 15 volts. The moment op-amp reaches 15 volts, now it is saturating. It cannot increase anymore. Okay, so ideally if the op-amp was not saturating, it would have just increased linearly. It would have just increased linearly to infinity. But because it's saturating, it has come to 15 volts. It has come to a zero gain point. So if you look at the op-amp's characteristic, it's going to look like this. So it has come to this point where the gain is almost zero. So feedback is, if the gain of the amplifier is zero, then A beta is zero, so which means there is no negative feedback anymore. At that point, the circuit goes to an open loop mode. So the circuit traverses through three different modes of operation. In the interval 0 to 0 plus to 0 minus, it is in a unity follower mode where the output voltages get precisely defined. There is no uncertainty there. That's very clearly 10 volts wherever you start from. And then after t greater than 0 to tau by 2, which is half a millisecond, the circuit is in proper integrating mode. It is behaving like an integrator. And when it reaches 15, it's going back to being in an open loop mode. After that, the voltage across the capacitors will be determined by an open loop charging. So that will happen through an RC discharge and charging, which will be an exponential charge or discharge, charging in this case. It will happen like an exponential charging. So that's the third charging, so which is t greater than tau by 2 or half a millisecond. After this, you will have an exponential charging. Once you see these three, you can immediately, we know how to intuitively write expressions for all the three different modes. It's in fact, we know till t equal to 0 and t equal to half a millisecond, we just drew the waveform. After that, it's an exponential charging. Okay, so that's what I've shown here. So this is the output voltage of the op-amp. It goes from 15, at t equal to 0, it goes to 10 volts. And then increases linearly because this increase is happening because of the capacitor voltage. So the op-amp output V0 is nothing but the capacitor voltage plus the resistor voltage, which is 10 volts here. The resistor's voltage is 10. So this is your output voltage. So if I have to find the capacitor voltage, all I have to do is shift this graph down by 10 volts. Right? It's just a 10 volts initially. Sorry, this is 10 volts till this point. Okay. I can simply shift the whole graph by 10 volts. You will get the capacitor voltage. So the capacitor voltage initially increases linearly from 0 millisecond to half a millisecond, which is tau by 2. After that, the circuit reduces to something like this. So you have output voltage at 15 and the capacitor is charged to 5 volts and the resistor, the other terminal is connected to the resistor to ground. So the circuit reduces to something like this. We have a 15 volt. So I can treat the op-amp's output like a 15 volt source. So remember, when the op-amp's output is saturating, I'm assuming it's just at the tip. So op-amp is still able to provide current for charging the capacitor even after it is saturating. Okay, so that's why I'm assuming it's at this point. So if the op-amp output is at this point, so generally it's assumed that the current that the op-amp can provide is also saturated, but we can assume that if it is in this region, it can provide infinite amounts of currents. Okay, so I'm assuming that it can provide any amount of current. So that's why I said it's in the tip. It's just at the tip where it's not gone into this region and it's also staying here, but it is at a point where it cannot interfere with the negative feedback anymore. Okay, but it is able to provide the current. It's able to provide the current to charge the capacitor. Okay, so if the op-amp is a negative feedback, it should ideally keep increasing, but it cannot do that anymore, right? So that's why I'm saying it's saturated, but it's able to provide the current. So then it's just going to behave like a voltage source, a DC voltage source of value 15 volts. And you have a capacitor which is initially charged to 5 volts. So when I say initially, now my origin is at half milliseconds. At half a millisecond, the capacitor voltage is at 5. Now we are interested in finding what happens after half a millisecond. Now this is a very trivial problem. You have a RC circuit with a capacitor voltage of 5 volts. Resistor is initially, the initial voltage across the resistor is 10 volts. Now we can see that in the steady state cap will act like an open circuit. So eventually the cap voltage has to be 15 volts and the voltage across the resistor will start from 10 and it will go down to 0, right? So as the capacitor gains all the voltage across the resistor will go down to 0. As the capacitor is fully charged to 15 volts at this point, resistor voltage is 0. Now all the while when the voltage across the resistor is going to 0 or the cap is getting charged, you can see that V plus, the non-inverting terminal of the op-amp, is at 10 volts and the inverting terminal is always at less than 10 volts, which is nothing but voltage across the resistor. That's always less than 10 volts, which means the output will always stay put at 15 volts. So there is nothing to disturb the equilibrium now. So that's why I said you can treat this like a voltage source. Okay, so now that we know this, the waveform can be easily drawn now. So the circuit is going to look something like this. I've shown here voltage across the resistor and capacitor. So at t equal to 0, if you recall, resistor voltage was initially at 0. It was suddenly raising to 10 volts. And it will remain there till half a millisecond. So this is where negative feedback is dominant. So when op-amp's negative feedback is dominant, you will have this condition V plus equal to V minus. So this stays at 10 volts. After that, it goes through a first order discharging. Now op-amp is completely inactive here. It's going through a traditional RC discharging. Op-amp is just providing the current that the circuit is demanding. Okay, I'm assuming even after it saturates, it provides that current. Now the voltage across the capacitor, on the other hand, it started from 0 initially. It increased linearly to 5 volts. So this is when the negative feedback was in action. After this, it's going to charge to 15 volts. So if you are to write an equation for the op-amp, it will be 3 different regions. So between 0 plus and 0 minus, 0 minus and 0 plus, it is at 0 volts. Vc of t is 0. Then Vc of t equals 10 by tau, which is Rc, 1 millisecond, times t. It's increasing linearly with time. This is true in this interval 0 plus to t to half a millisecond. So or tau by 2. At this point, op-amp's output saturates. Now negative feedback condition no longer holds true. It's an open loop. Then you have an exponential charging. So how do you find exponential charging? The initial voltage is 5 volts. The final voltage is 15. So your initial voltage is 5 plus Vf minus Vi, the V initial, times 1 minus e power minus t by tau. So it's an asymptotical charging. So this is the expression. So this you get it as 15 minus 10 e power minus t by tau. You can also derive this using the resistor. Because we know the voltage across the resistor, it's going to go from 10 to 0. So it will be 10 e power minus t by tau. And the input voltage is 15. So the voltage across the capacitor is 15 minus voltage across the resistor, which is 15 minus 10 e power minus t by tau. Just one thing to keep in mind, when I say t here, this t is t greater than half a millisecond. So ideally I should write t minus tau by 2. Tau by 2 is half millisecond here. E power minus of t minus tau by 2 by tau. Okay, I've shifted the whole graph by half a millisecond. So all it means is that the exponential charging is happening after half a milli, right? So it's before that it's linear charging. So it's a discontinuous function. The voltage across the capacitor is discontinuous. It's initially 0, then it ramps up, then it goes through an exponential charging. Now, if you know all these equations, it's very trivial to find this problem, right? Solve these problems. It's given that you're supposed to find out, this is the voltage across the capacitor. You're supposed to find out at t equal to 1 millisecond. 1 millisecond is one time constant, tau. So what you end up getting, 15 minus 10 e power minus of tau minus tau by 2 by tau, which is e power minus half. You get 15 minus 10 over square root e. I think that turns out to be 8.935. So that's it. I think there is no confusion in this problem. I thought I'll just explain it once. In case you have any doubts, post your questions in the comments section. I'll get back to you once I have some time. I'll definitely get back to you. Thank you.